Hello and welcome to my video. Last week, in this video, we have solved the locus problem where we have calculated the locus of the local maximum point of a changing function. You can find a link to that video on top right corner or in the description. In this video, we are doing that exact same thing again, but with a different function. So let's jump right into it. So it says find the locus of the local maximum point now with the function x squared e to the power of tx, where this real number t is called the parameter. Okay, so it is worth reminding the goal of our work here once again. If we plot our function here using the Desmos Graphing Calculator, you can clearly see that the local maximum point of fx changes as t changes. And it looks like the collection of these local maximum points constructs a curve denoted here in black dashed curve. This curve is called the locus, and we have to find that locus. So let capital letter x, y be the local maximum point of function fx. Then finding the locus of x, y means finding the relation that these two variables satisfy, such as this f in y equals fx. So let us do that. In order to find the local maximum, we must first differentiate. Here, using the chain rule, we have the derivative of x squared, which is 2x times e to the tx, plus x squared times derivative of e to the tx, which is t times e to the tx. And this gives tx plus 2 times x times e to the power of tx. Since this e to the tx is always positive, we have quadratic function tx plus 2 times x multiplied with some always positive term. And the derivative is 0 when x equals 0 or tx plus 2 equals 0. That is, when x equals 0 or when x equals minus 2 over t. But since this t is changing and even can have a value of 0 as well, it is undetermined that which is greater between 0 and minus 2 over t, or this minus 2 over t is even possible. Therefore, depending on the value of t, there are 1, 2, and actually 3 possible cases, and they are like this. So these are all 3 possible cases for the graph of f prime x, the derivative. Now let's take a look one by one. Case 1 is when 0 is greater than minus 2 over t, so t is greater than 0. Here the sign of the derivative is positive here, negative here, and positive here. So the graph of fx looks roughly like this. And you can see that the local maximum occurs at x equals minus 2 over t. The second case is when 0 is less than minus 2 over t, so t is negative. And here we must be careful. When t is negative, the derivative f prime x has negative leading coefficient in polynomial part because of this t right here. Therefore, the graph of the derivative is now somewhat altered compared to case 1. So now the derivative is negative here, positive here, and negative here. So the function fx decreases, then increases, then decreases again. Therefore, the local maximum still occurs at x equals minus 2 over t, the same as case 1. Finally, case 3 is when t equals 0. In this case, the derivative simply becomes 2x, so the derivative is negative here, positive here, and only 0 at x equals 0. This means that fx first decreases, then increases. So therefore, in this case, fx does not have a local maximum point. So these are our 3 cases. And now let us find out the equation for the locus in each case. In case 1, when t is positive, the local maximum occurs at x equals minus 2 over t. The local maximum value is f minus 2 over t, which is, if you calculate it, 4 over e squared t squared. And this local maximum point is denoted as capital letter x, y. So we have x coordinate as minus 2 over t and y coordinate as 4 over e squared t squared. In order to find the relation between x and y, we have to eliminate parameter t. From here, t equals minus 2 over x, and if we substitute this t in here, we obtain y equals, which is y equals x squared over e squared. from t being positive, and from here we have the domain x is less than 0. So we have this equation for the locus. Moving on, when t is negative, minus 2 over t is greater than 0. However, we have already seen that the local maximum still occurs at x equals minus 2 over t. So that the local maximum value is still f minus 2 over t, which is 4 over e squared t squared, which is the same expression as in case 1. Therefore, expressions for capital letter X and capital Y are the same, so that the equation of the locus is also the same. The only difference is that now t is negative, so from here, the domain now becomes x greater than 0. So this is our locus in this case. And finally, when t equals 0, we have already seen that fx does not have local maximum in this case. Therefore, if we combine cases 1 and 2, the equation of the locus is y equals x squared over e squared, where x is non-zero. The case 1 is when x is negative and case 2 is when x is positive. So the case where x equals 0 is not included. And since this capital X and Y are the notation that I have arbitrarily introduced, we can just change it into the more common small x and small y and say that the locus is this. Note that the locus is quadratic function. So if we plot this, we obtain this graph. And since x is not 0, this point right here, 0, 0, is excluded from the locus. Alright, so that is the answer, but just like my last locus video, let us do the visual demonstration using the Desmos Graphing Calculator again. Alright, so the red curve is the original curve y equals fx, and the black curve is the plot of the equation of the locus. Y equals x squared over e squared. For case 1, when t is positive, you can see that the local maximum point moves on the left part of the parabola where x is negative. For case 2, when t is negative, you can see that the local maximum point moves on the right part of the parabola, which is x being positive. And for case 3, when t equals 0, you can see that fx does not have the local maximum point. So this 0, 0 must be excluded from the locus. So that was another locus problem that I have prepared. Hope this video helped some of you understand the concepts about derivative and local maximum and locus a bit better. And if it actually did, please consider pressing the like and subscribe buttons. As always, thank you for watching, and I will see you in another video.